Welcome everyone. Today we're going to be working on Lewis dot structures for ionic compounds. So what I want to show you first, so this lecture contains all of the Lewis dot structure information, but we're just going to go through it chunk by chunk. So each lecture video is only going to be one portion of it. At the beginning of this lecture, I want to show you that I did put in a bond type review. So there's information on ionic bonds, both their characteristics, their structure, and then how those ions form, like we talked about in the last class. And then for covalent, we talked about that as well. And then we're going to be talking about Lewis dot structure. So this picture down here at the bottom won't make a lot of sense right now, though the information is all true and good and all of that. The structure piece of it here at the bottom we'll be actually talking about next class. And then pulled out some information from the video that you guys watched on metallic bonds to review that information, and so that you had something concrete to review when you need to look back over that before the quiz. This also talks about how metals are malleable and ductile, and so I wanted to talk about this for just 1 second and particularly look over to the right, where you can see that in the metal the electrons are all evenly spaced between the positively charged nuclei, and that actually acts as a buffer between those positive charges so that they never line up and repel, and that's what allows metal to be shapeable. And then next to that, if we remember back all the way back here, ions actually form crystalline structures. These are called crystal lattice. And each one is unique, but they're all really rigid crystalline structures. So if we go back over here, you can see that in that crystalline structure here on the right where it says the ionic crystal, if crystals typically shatter, they're not shapeable in any way, shape, or form. And what happens is any movement is going to line up because those electrons and those positively charged nuclei are locked into their spot. If any movement is going to line up two negatives and two positives together, which causes immediate repulsion. And that's what you see when something shatters. It's a movement that aligns two same charged particles and causes immediate repulsion, and the physical outcome of that is shattering. Since the metals have these electrons that are buffering all evenly between those positively charged nuclei, they can just kind of slide along as they need to keep everybody surrounded and oppositely charged. So as a result, on the left here, you can see that we can actually force a metal rod into a die cast, which could shape it into whatever you need. In this case, this one is drawing that out into a wire. And it's never going to shatter because those electrons just move around as they need to keep everybody from repelling. So just wanted to point that out. The big thing with metallic bonds is their conductivity and ductility being a result of what we just talked about a second ago here, and that really there's a relationship. All of that is related to the sea of electrons, just that it becomes basically one giant electron cloud instead of individual electron clouds around each atom. So moving on, we talked about valence electrons in the last class, so that information is here. We talked about how that becomes an ion, and we talked about everything wanting to satisfy the octet rule, and that's the goal of bonding, whether you're bonding ionically or covalently. So we talked about the formation of an ion practice, and we did that in the last class. And then now what we're going to do is we're going to apply that to beginning to create Lewis dot structures for ionic compounds. So in order to do that, we have to be able to do a Lewis dot structure for each one individually, each atom individually. So what we're going to do is we're going to identify the number of valence electrons for the atom. We're going to put the symbol for the atom in the center, and then we're going to place those valence electrons around that symbol in pairs, but we're still going to follow Hund's rule in that we evenly distribute before we pair. For ions, we're going to represent any transferred electrons with an X instead of a dot. So when we look at this, these individual Lewis dot structures, what we're going to see is we're going to put calcium's symbol in the middle here, and then we're going to place calcium's valence electrons around. Remember, we only care about the valence electrons. So calcium has 2 valence electrons, and so we're going to follow Hund's rule and evenly distribute. So we've got 1 here and 1 here. Now, oxygen has 6 valence electrons. So again, we're talking about valence electron and not charge right now. So for oxygen, we're going to put oxygen's symbol in the middle, and then we're going to evenly distribute 6 valence electrons. So notice that I distributed the first 4 evenly, and then I came back and paired 2 of them to get 6. So there's oxygen's Lewis dot structure by itself. Argon is one of our noble gases, so we know that it has 8 valence electrons. And so we know that it's going to have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons all the way around for its Lewis dot structure. So individual Lewis dot structures are the first step to writing a Lewis dot structure for an ionic compound. So we're going to switch over to that right now and go to the next slide. So ultimately what we're going to be doing is represented in this picture down in the bottom right. And so the first thing that we're going to do is we're going to identify our metal and our non-metal. And the metal is going to go, you can see calcium is our metal down here in the bottom right, and so it goes on the left-hand side. And then chlorine is our non-metal, and it gets written on the left-hand side. That mirrors how they are arranged on the periodic table. So we stick with that all the way through. So we're going to count the valence electrons for each of them, and we're going to write the metal on the left and the non-metal on the right. We're going to do individual Lewis dot structures for each of the atoms. So we're going to draw their valence electrons around each of them. And then because ionic compounds transfer electrons, we actually draw arrows to show that that no longer belongs to that atom anymore. You can see on this one that chlorine has a spot open for 1 more on each of those chlorines. Remember that bonding is all or nothing. So calcium has to give away both of those electrons or none at all. So chlorine is an okay match. There's 1 spot open, but we need 2 chlorines because we need 2 spots for 2 electrons. Drawing arrows to those spots where they're going to eventually be located. And for our purposes, in the end, we are going to represent these electrons that came from somewhere else as an X. So calcium's electron came over here to chlorine. Calcium's electron up here came over here to chlorine. The last thing that we're going to do is simplify this. So we've got each electron here, and that was given to chlorine. But this big compound here at the end looks kind of messy, and we can bring those 2 chlorines together by putting them in brackets. So what we're going to do is we're going to keep calcium as 2+, just like it is, and notice that it doesn't have any electrons anymore because it gave both of them to chlorine. Well, there's 2 chlorines, and I'm actually going to simplify that down to 1. So each chlorine had 7 valence electrons of its own, and then each chlorine received 1 from calcium. Each chlorine is negatively charged, but I have 2 of them. So this would be my final answer, simplified, to look ultimately like the formula we would create. We'll talk about that in the next unit. So notice that our crisscross matches too. So remember the crossover method that we were doing last time. Chlorine has a negative charge with a 1 assumed attached to it, and that comes down onto calcium, so we have no subscript. calcium has a 2+ charge, so the 2 comes down on chlorine, matching, or giving it the 2 subscript. So our crossover method being used to check this is really, really helpful. So what we're going to do is we're going to do some practice. We're going to do magnesium and fluorine. So magnesium has 2 valence electrons, so it's easier to get rid of 2 than gain 6, so it's going to make a 2+ charge. And fluorine is going to have 7 valence electrons, so it's easier to gain 1, so it's going to have a 1- charge. So we look at this, and magnesium has 2 valence electrons, and each fluorine, how do I know that I need 2 fluorines? Let's look at this really quickly. So I'll start with just 1. Fluorine has 7 valence electrons, which only gives it 1 space open. So just like calcium, remember, it's an all or nothing deal. So that tells me that I'm going to need 2 of them because I need 2 spots open. Now, I could have also known that from my charges. If I crisscross them, that tells me that magnesium is going to need 1 and fluorine is going to need 2 from crisscrossing. So again, we have that to use to double check. So remember, we draw our arrows showing where the electron is going to go. And then from there, we simplify. Magnesium has now lost all of its valence electrons, so it does not have any more, and it has a 2+ charge. Fluorine, I'm going to simplify into brackets because there's 2 of them. I'm going to give it all of its valence electrons, and then I'm going to give it the one that it received from magnesium, and then each of them is a 1- charge, and I did that 1 time and 2 times, so I'm going to put a subscript of 2. Again, that matches my crisscross. Let's look at potassium and sulfur. Potassium is a 1+ charge because it has 1 valence electron. Sulfur is a 2- charge because it has 6 valence electrons, so there's 2 spots that are more easily filled than losing those 6. So we're going to draw their initial valence electrons individually. And sulfur has 6. 1, 2, 3, 4, 5, 6. Okay, so we can tell right away that sulfur has 2 spaces open, a space right here, on top of each of the individual electrons on the side. But potassium only has 1 to give. So that fills up that one, but what do I do about the other one? Again, this is what tells me I'm going to need a second potassium to fill that up. Does that make sense when I look at my crisscross? If sulfur is a 2-, that tells me that I'm going to need 2 potassiums. So when I simplify, potassium got rid of both of its electrons, or both potassiums got rid of its electrons. So I don't have to put this in brackets because there's no electrons to enclose. There's no electrons to package. Potassium, each of those potassiums gave away their valence electrons. But sulfur was on the receiving end. So sulfur has 1, 2, 3, 4, 5, 6 of its own, and then it has the 2 that it received from potassium, both of the potassiums. This would be my final answer, and again, I don't need to put potassium in brackets because there are no electrons left to package. The last thing that I want to point out is please remember that always your metals are losing their electrons, and always your nonmetals are gaining the electrons. So your metals should not have any electrons on them in the end. We're going to continue practicing together in our homework packet, so go ahead and take that out, and then we'll transition that direction.